Yeah, just sing that.
I'm on top of the world. Wait, how does that song go? Nick Genovese here. What?
Best video. Oh.
No. Hi, Nick Genovese here. So, what are rockets? What makes them tick? Today we'll be exploring one-dimensional motion using this rocket to calculate velocity. Join me on this journey. From infinity to beyond. To get started, these are the materials we will need. First, you will need the rocket and its base, a bicycle pump, a meter stick, and various valves of different strengths to cause different pressures within the rocket. This is how to assemble your rocket. Begin by securing the bicycle pump valve onto the opening on the rocket's base. Then, select the valve of your choice and securely push it onto the opening of the top of the rocket base. Next, take the body of the rocket and push it on so the valve and the body are conjoined. Place the nose of the rocket onto the body. Congrats, you can set up a rocket. Before we start, we must go over some safety precautions. Do not stand directly over the rocket during launches. Do not swing your meter stick around at any times. Do not try to catch the rocket. Always be aware of your surroundings and keep distance from other groups. Do not throw your rocket. Always wear safety goggles.
Disregard these safety precautions. There is a serious economic injury, such as making eggs, larger, and will be learned for the remainder of the year. To avoid long-term injury, please keep distance on injury less than 1 to 4 hours. Stop putting distance due to stress, and rest of loss of vision pressure.
Now, let's start the trials. First, the low valve. Next, the medium valve. Two, one. And finally, the high valve. Now that we have the data, let's move to the calculation.
To start the calculations, we're going to calculate the average time for each trial. To do this, you're going to add up time 1, time 2, and time 3, and divide it by 3. For low, we get an average time of 4.43 seconds. For medium, we get an average time of 5.01 seconds. For high, we get an average of 5.58 seconds. Next, we're going to calculate the time it takes to go up. To do this, you're going to take the average time you found earlier for each trial and divide it by 2. For low, the time up will be 2.22 seconds. For medium, the time will be 2.51 seconds. For high, the time will be 2.79 seconds. Next, we're going to find the initial velocity. You do this by using the equation v equals v0 plus at. During its launch, the rocket follows a parabolic path. At the top of its path, at the apex, velocity equals 0 meters per second. So you plug in 0 meters per second for v, v0 is what you're trying to figure out, acceleration is negative 9.8 meters per second squared due to gravity, and you plug in your time. For low, it's 2.22 seconds. Therefore, through calculation, you get 21.8 meters per second as your v0 for the low trial. For the medium trial, after plugging in 2.51 seconds, you reach 24.6 meters per second as your initial velocity. For the high trial, after plugging in 2.79 seconds, you reach 27.3 meters per second as your initial velocity. Now we're going to find the final velocity. In one-dimensional motion, final velocity is equal to the negative initial velocity. This means that they share the same magnitude but different direction. For the low trial, since the velocity was 21.8 meters per second, the final velocity with the negative in front of it would be negative 21.8 meters per second. For the medium trial, 24.6 meters per second was initial velocity. Therefore, the final velocity is negative 24.6 meters per second. For the high trial, the initial velocity was 27.3 meters per second. Therefore, the final velocity would be negative 27.3 meters per second. To find the maximum height, we're going to use the equation delta y equals 1/2 at squared plus v naught t. Delta y means the change in displacement, in this case the change in height. Acceleration is negative 9.8 meters per second squared due to gravity. We're using time up because we know at time up, that is the apex where velocity equals 0, and that is where the maximum height is. We know v naught from our earlier calculation. For the low valve, after plugging in 2.22 seconds and 21.8 meters per second, we receive 24.2 meters as a maximum height, or the change in displacement. For the medium trial, after plugging in 2.51 seconds and 24.6 meters per second, we receive 30.9 meters to be the maximum height, or change in displacement. For the high trial, after plugging in 2.79 seconds and 27.3 meters per second, we receive 38.0 meters as a change in displacement, or maximum height. Next, we're going to calculate uncertainty. Because there are 25 frames per second, each frame is equivalent to 0.04 seconds. Therefore, the uncertainty is equal to plus or minus 0.04 seconds. The first step is to calculate the percent uncertainty. Percent uncertainty is uncertainty over the actual times 100. In this case, uncertainty 0.04 seconds over the actual time. Because we have 3 different times, we must calculate percent uncertainty for each time. For the low trial, the first time was 4.01 seconds. After calculating, we receive 1.00% to be the percent uncertainty. For the second time of the low trial, we received 4.86 seconds. After calculating, we received 0.82% as the percent uncertainty for the second time. For the third time, the time was 4.43 seconds. After calculating, we received 0.90% to be the percent uncertainty of the third time. The next step is to calculate the measurement. We already did this earlier when we calculated the average time for the low trial, which is 4.43 seconds. The third step is to add the percent uncertainties together. For this low trial, the first percent uncertainty was 1, second percent uncertainty was 0.82, and the third percent uncertainty was 0.90. Added together, you receive a total percent uncertainty of 2.72%. The total percent uncertainty is the final uncertainty for all calculations because all other calculations do not have any variables that have their own individual uncertainty. In this whole entire calculation in lab, the only uncertainty is with the time. Next, we go through the whole process again, but with the medium trial. For the first time, the time is 4.93 seconds. After calculating, we receive 0.81% to be the percent uncertainty for the first time. The second time is 5.06 seconds. After calculating, we receive 0.79% to be the percent uncertainty for time 2. The third time is 5.05 seconds. Upon calculating, we receive 0.79% to be the percent uncertainty for time 3. Next, we're going to calculate the measurement. We did this earlier and we received the average time to be 5.01 seconds. After that, you're going to add the percent uncertainties together. 0.81% plus 0.79% plus 0.79% equals to 2.39%. With all these calculations, what have you learned? Let's go straight into analysis.
Hi. The data shows that as the trials increased from low pressure to high pressure, the total time, on average, increased from 4.43 seconds at the low valve to 5.01 seconds on the medium valve, and finally to 5.58 seconds at the high valve. Additionally, the initial velocity increased as the pressure went up from 21.8 meters per second on the low valve to 24.6 meters per second and finally 27.3 meters per second on the high valve. This makes sense because logically, the higher the rocket goes and the more distance it covers, the more time it should take in the air. It should be noted that when measuring altitude, we measured from the bottom of the rocket, not from the ground. As shown in the graph to my right, acceleration stayed constant at negative 9.8 meters per second. The position, or altitude, followed a parabolic path, steadily increasing and then decreasing in correspondence to the pattern that would be observed when the rocket is launched. As the rocket rose, the velocity decreased in magnitude until the apex was reached. As it began to fall, the velocity increased in magnitude as time progressed. For calculation purposes, we developed our own procedures for determining the actual velocities of the rocket using a digital camera. We calculated the velocity by shooting the rocket up against a meter stick to measure the height, and then noted the height increase per frame. Data was generated using this method, and then graphs were created that exemplified the rocket's velocity, altitude, and acceleration as a function of time in the high trial only. An object in freefall experiences an acceleration of negative 9.8 meters per second squared. The negative sign indicates the downward acceleration. Whether explicitly stated or not, the value of the acceleration in the kinematic equations is negative 9.8 meters per second squared for any free-falling object. If an object is merely dropped, as opposed to being thrown, from an elevated height, then the initial velocity of the object is 0 meters per second. If an object is projected upwards in a perfectly vertical direction, then it will slow down as it rises upward. The instant at which it reaches the peak of its trajectory, its velocity is 0 meters per second. This value can be used as one of the motion parameters in the kinematics equations. For example, the final velocity after traveling to the peak would be assigned a value of 0 meters per second. If an object is projected upwards at a perfectly vertical direction, then the velocity at which it is projected is equal in magnitude and opposite in sign to the corresponding velocity at which it returns to the ground. That is, a ball projected vertically with an upward velocity of 30 meters per second will have a downward velocity of 30 meters per second when it returns to the same height.